Today, I'm Joseph Del Rosario, MS Chemistry. And for week 6, here my presentation for potentiometry. So the contents of this study are definition, principle, ion selective electrodes or the ISE, general method, application of potentiometry and potentiometric titration, sample computation using Nernst equation. So for the definition, potentiometry is a field of electroanalytical chemistry in which potential is measured under the condition of no current flow. It is a method of analysis in which we determine the concentration of a solute in solution and the potential difference between two electrodes. Potentiometry is an instrument that's used for the determination of unknown concentration between the reference solution and the sample. So for its principle, the principle involved is when a pair of electrodes is placed in a sample solution, it shows the potential difference by the addition of diaphragm. So in this way, a potential difference is set up with the electrode and solution. So metal ions may dissolve in the solution as positive ions leaving electrons in the electrode. Also, metal ions may take up electrons in the electrode and get deposited as neutral atoms. So here are the types of electrodes in potentiometry. First, the reference electrode is a half cell having a known potential. Examples are SHC, standard hydrogen electrode, and silver chloride electrode. For the reference electrode, it has a constant potential. The electrode potential of the SHC, zero at all temperature. It is also the electrode that maintains its potential and remains stable when dipped into a sample solution. For the next sample is indicator electrode, is another half cell which unknown with unknown potential. Potential of this indicator electrode is directly proportional to the ion concentration. So examples are metal electrode, uh, uh, selective electrode (ISE). For the also indicator electrode when immersed in an analyte solution, its potential is sensitive to the concentration of analyte. An indicator electrode is electrode that responds to the variation in the potential of analyte solution. Again, for further definition of reference electrode, here the example SHC is composed of inert solid platinum on which hydrogen gas is absorbed, immersed in solution containing hydrogen ions at unit activity. This is the reaction. So this is an illustration of standard reference electrode. This is the salt bridge to the indicator electrode, the analyte solution immersed with the SHC. Another example of reference electrode is the SCE, saturated calamine electrode. Is a half cell composed of mercurous chloride in contact with mercury. This is the reaction. Another is a silver chloride. The silver chloride reference electrode is composed of silver wire, sometimes coated with a layer of solid silver chloride immersed in a solution that is saturated with potassium chloride and silver chloride. And here is the solution of the equation for the silver chloride. So another for standard calomel, these components are either layered under a saturated solution of KCl within a freighted compartment surrounded by saturated potassium chloride solution. So for the silver chloride electrode, standard cell potential is two positive 222 volts, and for SCE, the standard cell potential is positive 244 volts. Here is the illustration of these two sample electrodes. And now for the indicator electrode, the most common is the ISE, ion selective electrode, also known as specific ion electrode. Is a transducer sensor that converts the change in the potential concentration of a specific ion into solution in solution into an electrical potential. So ISE, the voltage is theoretically dependent on the logarithm of the ionic activity according to the Nernst equation. So ISE are used in analytical chemistry, biochemical and biophysical research, which measurements of ionic concentration in an aqueous solution are required. So here is the sample of indicator electrode ISE. It is immersed in an analyte solution. The types of ISE are the following: gas membrane, solid state membrane electrode, liquid membrane, and gas sensing electrode. Next slide. The electromotive force of the complete cell is given with the following equation. E cell is equals to E reference plus E indicator plus E junction. The definition of this: E reference is the electromotive force of the reference electrode. So E indicator is the electromotive force of the indicator electrode. E junction is the electromotive force at the junction of the liquid. So another part of the uh, potentiometric cell is the salt bridge. It defines the, as the laboratory device used to connect two half cells of galvanic or voltaic cell. Salt bridge should be inert. It should not precipitate also. So it should not react with anode or cathode solution. A salt bridge containing an inert electrolyte such as potassium chloride. It connects two half cells. The end of the salt bridge are fixed with porous frits. Uh, Here is the illustration of salt bridge. So going back to the salt bridge, it connects the two half cells. As I've said, the ends of the salt bridge are fixed with porous frits, allowing the electrolyte ions. These are the porous frits, uh, allowing the electrolytes ions to move freely between the half cells and the salt bridge. These are the half cells, the anode or the cathode. The anode is the reference electrode, and the cathode is the indicator electrode. Also, this movement of ions in the salt bridge completes the electrical circuit. So it is a bridge. Next slide. We will now go to potentiometric titration. Here's a sample of potentiometric titrator. I used this before in my previous job. It is similar to direct titration. No chemical indicator is used. Instead, indicator electrode is used during titration. So unlike in, for example, the acid-base titration, where we use phenolphthalein or methyl red. Here, we don't use it. We will just use the indicator electrode to indicate the endpoint of the titration. So a pair of electrodes are placed in a sample solution or analyte. The types of potentiometric titration: acid-base, redox titration, complexometric titration, and precipitation. And its applications are clinical chemistry for the analysis of metals, and for the analysis of cyanide and ammonia in water or wastewater, in agriculture for the detection of different fertilizer, elements in soils and fertilizer. So it is also used in detergent manufacturing, uh, and food processing, etc. So potentiometric titration, to add more definition, belongs to chemical methods of analysis in which the endpoint of the titration is monitored by the indicator electrode that records the change of potential as a function of amount, uh, usually expressed in volume, of the added titrant of exactly known concentration. So here, in potentiometric titration, a salt bridge is used to prevent interference of the analyte with the reference electrode. So now we will go to Nernst equation to give you some example of the uh, computation using potentiometry. Here is the Nernst equation. E uh, below are the E is the uh, instantaneous reaction. E naught is the standard cell potential. R is the ideal gas constant. And T is temperature either in centigrade or in Kelvin. We will assume the reaction takes place at 25 degrees Celsius or 298 Kelvin. N is the number of electrons transferred. F is Faraday's constant. Q is the reaction quotient. So this equation has a simplified form for easier computation. Here, uh, we just divided the value of R, value of Faraday constant, temperature either in 298 Kelvin or 25 degrees Celsius. So that's why we got this 0.592 volts. And instead of natural logarithm, we use the logarithm of 10 of the reaction quotient Q. So for the examples, we will use the reaction of zinc and copper and copper cell. We will now compute the instantaneous cell potential. Here, zinc is oxidized into zinc 2 plus. Copper 2 plus is reduced to copper solid with a standard cell potential of 1.10 volts. So copper 2 plus has a concentration of 1 molar, and zinc also has a 1 molar concentration. So using the this equation at 25 degrees Celsius, here the reaction quotient, uh, we will divide product by the reactant. So we will have the equation of zinc 2 plus over copper 2 plus. For Q, we need to think about the reaction quotient Q as the same for the equilibrium constant, so expression. So if we think of the balance equation, here's the balance equation. Uh, Pure solids are left out of the equilibrium constant expression. So it would be the concentration of product over the concentration of the reactants here. So dividing 1 molar over 1 molar is equals to 1. So as we know, logarithm of 1 is 0. So the whole half value of this will be 0. So the we will have the instantaneous potential of 1.10. Si 0 nga itong yung other half part of the equation. So another example, zinc again, solid zinc plus copper 2 plus, again with the standard cell potential of 1.10 volts. Copper 2 plus has a concentration of 10 molar, and zinc 2 plus with a concentration of 1 mole. So using the equation again at the 25 degrees Celsius condition, uh, again from using the reaction constant product over reactant, so zinc 2 plus over copper 2 plus will be 1 over 10, this was zero point 0.1, so Q is less than 1. So applying the nearest equation, we will have a negative result if you have a value of less than 1. So logarithm of zero point 0.1, so we will have a negative result. So here we will add up to the value of the 1.10 volts. So we will have the result of 1.13 volts. See, around ano to, 0.03, 0.029. So rounding up, naging 0.03 na lang siya. So the result is 1.13, positive 1.13 volts. Next slide, next example again, third example, same equation, same value of standard cell potential 1.10 volts. So we have a different concentration here. Copper has 1 molar, zinc with 10 molar, applying the equation. So again, product of reactant 10 over 1, zinc 2 plus over copper 2 plus, we will have 10. So Q is greater than 1, so that logarithm of more greater than 1 is a positive result, giving a positive result. So we will now subtract 1.10 volts to the value of with a negative value. So around 0.03. Hindi ko na po kinumpute. Yung nilagay yung value. So the final result of instantaneous potential is 1.007 volts. So here the example of example computation using Nernst equation. Sa summary of the potentiometry, it is the potentiometric titration is a laboratory method to determine the concentration of a given analyte. Second is it is used in characterization of acids. It is in this method there is no use of chemical indicator. Instead, electric potential across a substance is measured. Last is in this technique the potential uh, between two electrodes is measured using high impedance voltmeter. So thank you for listening. Here's my presentation. Good day, all. Good day again.